Hi, it's Mr. Andersen, and this is AP Physics Essentials, video 97. It's on rotational inertia. When an object is rotating, like the flywheel on this tractor, it has a certain amount of angular momentum, and that's made up of the angular velocity, how fast it's spinning, and also this rotational inertia of the object. But to calculate the rotational inertia, it's going to depend on what that object looks like. And this flywheel has a large amount of mass that's distributed far away from that point of rotation. And so it's going to have a large rotational inertia. And it's a great place where we can store energy as the engine's idling, or we could even start the engine using that flywheel. And industry is starting to use industrial flywheels as a place in a factory where we can store a certain amount of energy. And so angular momentum of a system is based on two things. It's the position of all the objects, and that's going to be its rotational inertia, and then the velocity of all of those objects. And so due to the conservation of angular momentum, if we change the position of where those objects are, we're not going to get new momentum, and so what we're going to do is see changes in the velocity of those objects. And so remember, momentum of a particle that's moving, P equals mv, where m is mass and v is the velocity of the object. But what if the object isn't moving through space? Let's say it's just rotating. It still has momentum. We call that angular momentum, L, and that equals to I times omega, where omega represents the angular velocity, how fast it's rotating. And then I is very similar to the mass. It's this rotational inertia. And in fact, mass is a large part of that. And so let's say we have a record that's spinning. So it has a certain amount of angular momentum. And I simply just want to stop the record. Well, what makes it harder for me to stop the record? It's rotational inertia and the velocity at which it's spinning. Now, that rotational inertia is made up of two things: the mass of the record, or the turntable in this case, and also the radius, how far it is from the center point. And if you needed to calculate it, this is the formula for rotational inertia. And so I equals 1/2 mr squared. And so if we were to just try this with a record, the mass of a record is 1/10 of a kilogram, so 0.10 kilograms. And then the radius from the center point is going to be 15 centimeters, or 0.15 meters. And so using that formula, I could calculate my I, or rotational inertia, to be 1.1 times 10 to the negative third kilogram meters squared. And in AP, they'll have to give you the formula for various objects if they want you to calculate rotational inertia. Let's say, however, we were to change that record and we were to have all of the mass on the outside of the record. Well, we'd have to use a different formula. Instead of it being 1/2 mr squared, it's actually going to be mr squared. And so we're not taking it times 1/2. And so by positioning that mass on the outside, what have we done to our rotational inertia? We've actually doubled it. And so if we get it going at the same speed, it's going to have twice the angular momentum. And now you can start to see why flywheels have their mass distributed to the outside. And so the inventor Da Vinci came up with a flywheel that's variable. And so as it would rotate, these spheres would be lifted up and they would start to move to the outside. And so if you think about it, what's going to happen to our rotational inertia as the mass is all moving farther out from that center point? Well, I is going to increase as we start to crank this flywheel. Now, what happens when you let it go? Well, friction is going to slow it down. And so our angular velocity is going to start to drop. But what's really interesting about this is that as it starts to slow down, these spheres start to drop down. And so what happens to our rotational inertia? It actually becomes less and less. And so he designed this as a way that you could have a crank that keeps moving at a constant velocity. It's pretty smart. We would also see rotational inertia if we're looking at objects in orbit. And so if we look at a satellite as it orbits around the Earth, you can think of it as two objects that are connected. And so if we look at how long it takes to go around the Earth, it's around 90 minutes. But let's say we change what's orbiting. Let's say it's now the moon going around the Earth. It has a large angular momentum. The distances are so large that it takes around 28 days for it to go around the Earth. Let's say we were to look at the Earth as it moves around the sun. Again, it takes a year for it to go all the way around. But what would happen if we could magically grab the Earth and position it in a different spot and we conserve the angular momentum, well now, since that rotational inertia is so much closer to the middle, we're actually increasing the velocity, and so we're going to see a year that's going to be about half the distance of what it is. And we'd see the same thing if we look at planets that are closer to the sun. So did you learn to calculate the angular momentum of a rotating object? Remember, it's dependent upon the speed, but also this rotational inertia, which itself is determined by the mass, the radius, and what the shape looks like. And I hope that was helpful.